All right, let's talk about one of the absolute classic system design interview questions, the rate limiter. Getting this one right can literally be the difference between getting an offer and, well, not. So today, we're going to walk through a complete interview winning framework. We'll cover everything from the very first question you should ask your interviewer all the way to a design that can actually scale. Ready? Let's get into it.
So to really get a handle on this, let's start with a super simple analogy. Picture this. You're at an amusement park standing in front of the most popular roller coaster. There's a guard there who says, "Hey, you can only ride this twice today." That guard, that's our rate limiter. They're making sure things are fair and that the ride doesn't get totally overwhelmed. Now, in the digital world, a rate limiter does the exact same thing. It enforces the rules on how often a user can do something, like call an API. The only difference is it's doing this job at a massive scale. We're talking millions of times a second.
So you might be thinking, why bother with this digital guard? Well, let me tell you, for any system that's even remotely large scale, it's not just a nice to have, it's absolutely non-negotiable. First off, it stops your servers from just, crashing. Imagine a buggy script or a malicious attack sending a flood of requests. Without a rate limiter, your whole system could go down. It also makes sure one power user doesn't hog all the resources, so everyone gets a fair shot. And here's the big one for the business. It keeps your cloud bills from going through the roof. More requests mean more money, and a rate limiter puts a cap on that. Okay, so here's our game plan for acing this interview question. We're going to tackle this in 4 simple steps. First, we'll ask the right questions. Then, we'll sketch out the big picture design. After that, we'll get into the nitty-gritty and pick an algorithm. And finally, we'll level up by talking about how to handle the really tricky stuff at scale. All right, let's jump into our first step, and trust me, this is maybe the most crucial one. Before you even think about touching a whiteboard marker, before you draw a single box, you have to understand the problem you're actually trying to solve. Your interviewer isn't just looking for a solution. They want to see how you think. They want to see that you're the kind of engineer who thinks before they build.
And this quote right here, it perfectly captures the cardinal sin of system design interviews. So many candidates hear the prompt, design a rate limiter, and they just immediately start whiteboarding. That is a huge red flag. It tells the interviewer you're jumping to conclusions. The best engineers, the ones who get hired, always start by asking questions to really nail down the scope of the problem.
So what are these magic questions you should be asking? Well, start with the basics. Something like, okay, are we talking about a client-side or a server-side limiter? And you'll want to guide them towards server-side, right? Because you just can't trust the client. Then you'd ask, how are we identifying users to throttle? Is it by their IP, their user ID, maybe a device ID? You also want to think about the user experience. Should we let people know when they've been throttled? And finally, the big one for scale, does the system need to work across multiple data centers in a distributed environment? Okay, so once you've gotten answers to those questions, you can start laying out your goals. On the functional side, it's pretty straightforward. We need to limit requests based on some rules and tell users when they hit the limit. But it's the non-functional side where things get really interesting and really tough. This thing has to be bulletproof. We're talking 5 nines of uptime. It needs to be insanely fast because you can't add a bunch of latency to every single request. And of course, it has to be cheap enough to run without breaking the bank. Okay, requirements are locked and loaded. Now we can move on to step 2 and start sketching out the blueprint. This is where we draw the high-level architecture and figure out where all the major pieces of the puzzle go. And the very first and maybe most important architectural decision we have to make is, where does this thing actually live? Where in our stack are we going to put this rate-limiting logic? So you've really got 2 main choices here. Option 1, you could stick the rate limiter logic right inside your API servers. This gives you really fine-grained control, but it also adds extra work to servers that should be busy with, business logic. Option 2, which is the much better approach, and the one your interviewer is hoping to hear, is to pull it out into its own layer, as a middleware. Think of it like an API gateway. It's like putting a bouncer at the front door of your club. They check everyone before they get inside and bother the main event, which in this case are your backend services. And just to give you a sense of the scale we're talking about, we might need to handle up to 50 billion requests a day. That's a staggering number. And that's exactly why putting this in a separate gateway is so critical. Can you imagine trying to have every single one of your app servers handle that kind of decision-making overhead? It would be a total disaster. You absolutely have to shed that load at the front door. So here's what the journey of a single request looks like. A client sends a request. It doesn't go straight to the API server. Oh no, it gets intercepted by our rate limiter middleware first.
That middleware then does a lightning-fast check against a cache, something like Redis, to look up the user's current count. If they're under the limit, great, the request gets passed along to the actual API server. But if they're over the limit, the middleware just stops it right there and sends back that famous HTTP 429 too many requests error. The key here is that the main API server is never even bothered by the rejected traffic. All right, now we get to the really interesting part, the brains of the whole operation. How does this thing actually decide whether to allow or deny a request? This is where we need to roll up our sleeves and talk about algorithms. A fantastic algorithm to start the conversation with is the token bucket. It's super intuitive. Just imagine, every user gets a bucket. And we're constantly dripping tokens into that bucket at a steady rate, like say 10 tokens every minute. Now, every time that user makes an API call, they have to spend 1 token. If they try to make a call and the bucket's empty, sorry, request denied. It's really simple, it's light on memory, and it's actually pretty good at handling little bursts of traffic. Okay, another simple one you can bring up is the fixed window counter. The idea here is we chop up time into fixed blocks, let's say 1-minute windows. We just keep a counter for how many requests a user makes inside that 1-minute window. When the minute is up, poof, the counter resets to 0. It's super easy to explain and implement, but, and this is a big but, it has a major flaw. And here it is, that critical flaw. It's called the edge of window problem. Just look at this timeline. Let's say our rule is 6 requests per minute. Now, a user sends 5 requests at the 55-second mark. No problem, they're allowed. But then, just 5 seconds later, the clock ticks over, the window resets, and the counter goes back to 0. The user immediately sends 5 more requests, and they're allowed too. So what just happened? We let 10 requests through in just 10 seconds. That completely blows our 6 per minute rule out of the water. So how do we fix this? The answer is the sliding window algorithm. Instead of these hard, clumsy resets, it keeps a count over a rolling time period. It's always looking at, say, the last 60 seconds. Now, the best version to talk about in an interview, the one that really shows you know your stuff, is the sliding window counter. It's a really clever hybrid. It gives you all the accuracy of a true sliding window, but it uses some smart estimations so you don't have to waste memory storing a timestamp for every single request. It's the best of both worlds, highly accurate and super efficient. And you don't have to just take my word for it. This is what the pros use in the real world. Cloudflare, the company that handles a massive chunk of the internet's traffic, they put this exact algorithm to the test. Across 400 million requests, the accuracy was 99.997%. That's an error rate of just 0.003%. It's proof that you can get near perfect accuracy without killing your performance or memory. And bringing up this kind of data-driven trade-off in an interview, that's how you really impress someone. Okay, so we've picked our architecture, we've picked our algorithm, we have a good answer. But we don't want a good answer, we want a great answer. To really level up and show you're thinking like a senior engineer, you need to talk about the gnarly, complex problems that only show up at massive scale. First on that list, race conditions. This is a classic concurrency problem. Just imagine this. What happens if 2 requests from the same user hit 2 different servers at the exact same time? Let's say the user's count is at 99, and the limit is 100. Both servers could read the value 99 at the same time. Both think, great, there's 1 slot left, and they both let the request through and update the count to 100. The problem is, we just let 101 requests through, not 100. It's a super subtle bug, but at scale, it's a very real problem. So how do you solve that? The standard answer here is to use locks. Basically, when the first request comes in to check the counter, it puts a temporary lock on that user's record. Now, if that second request shows up at the same millisecond, it can't do anything. It has to wait in line. Only after the first request is completely finished, reading the value, updating it, and then releasing the lock, can the second request take its turn. This forces everything to happen one at a time, in order, which guarantees the count stays perfectly accurate. Okay, but what about a truly global system? With servers all over the world. If your server in Europe has one counter and your server in Asia has a different one, your whole system is basically broken. A clever user could just send requests to different regions and completely bypass the limit. So the solution is you need a single source of truth. All of your rate limiters, no matter where they are on the planet, have to talk to one centralized data store, like a shared Redis cluster. This is the only way to make sure the limit is enforced consistently everywhere. And there you have it. That's the complete interview-winning framework. Let's recap it one more time. 1. Clarify. Always start by asking questions. 2. Design. Sketch out that high-level architecture with a middleware gateway and a cache like Redis. 3. Algorithm. Compare the different options and confidently choose the sliding window counter, explaining why. And 4. Scale. Prove you're a senior-level thinker by tackling the hard stuff like race conditions and distributed state. And just to leave you with one final thought to chew on, this pattern is way more powerful than just throttling user API calls. Think about it. Where else could you use this? What about limiting failed login attempts to prevent brute force attacks, or slowing down new account creations to stop spam bots? You could even rate limit expensive database queries to protect your backend. The applications are everywhere. It's a fundamental tool for building stable and secure systems. Thanks so much for tuning in.